Let me present a study on the topic the build on Feistel network architecture block Cyper modifications by the author Inna Rozlomii, Andrei Yermilko, and Sergei Naumenko. The study considers the method of implementation Shannon's idea for building a cryptography stable system by repeatedly applying relatively simple cryptographic transformations. It is suggested to reduce the sensitivity of existing cryptographic algorithms to existing cryptanalysis tools by implementation a universal solution suitable for increasing any encryption algorithm's cryptographic stability. The widespread use of iterative ciphers and the development of compiler power create a whole range of threats to the cryptanalysis of ciphers. Providing cryptographic security is one of the critical aspects of a cryptographic algorithm. The first generation of block ciphers has a simple key layout. It usually includes only a combination of bits or bytes of the encryption key, as in DES. This method of obtaining the round keys has advantages in hardware and software implementation, but it is vulnerable to some types of cryptanalytic methods. For example, sleight attack, full sweep attack, differently cryptanalysis, and other types of attacks. Thus, it is important to increase the stability of cryptographic protection algorithms. This study considers the possibility of solving this problem by modeling the multivariate encryption algorithm. The building a cryptographic method suitable for improving any encryption algorithms. Its main property is to increase cryptographic resistance by increasing the length of the key and the length of the block of information. Usually, we get an asymptotic statistical portrait of the output encryption information as a result of encryption with existing symmetric iterative algorithms. In a particular, Kalina AES, DES as a rule. Another disadvantage of round cryptographic algorithms is the encryption time, which depends directly on the number of rounds. The sensitivity of existing cryptographic algorithms to various types of cryptographic analysis actualizes the need for their improvement. An adequate solution is the development of a single universal solution for improving any cryptographic algorithm to increase cryptographic stability by increasing the length of key and the length of the encrypted information block. There are two most common approaches to building block ciphers. Ciphers based on the architecture of the Feistel network and the permutation network. Rounds of algorithms built on the architecture of Feistel network encryption blocks of information in the following way. First, the block is divided into two equal parts. Then the right part is transformed by the function f, which depends on the subkey, and summed module 2 with the left part. Then these parts change places. The Feistel network, such as shown on the slide, good because encryption differs from decryption only in the order of keys, and the round function can be any. Various modifications of the Feistel network appeared over time, such as shown on the slide. The main reason for this is the focus of the classic Feistel network on 64-bit blocks. Therefore, problems arise when converting information with 128-bit blocks, since most platforms on the modern computers are 32-bit. In this regard, the block must be divided into two parts and four. On this slide, we are watching a spin network. As a substitution permutation network allows you to transform information in one round. One round of such a cipher consists of these reversible transformations, addition with a subkey, non-linear substitution, and termination of bits. Most existing encryption algorithms use multiple rounds of encryption to improve the statistical characteristics of cipher. There is re-encryption of the block of information is used. However, according to Shannon's theorem, a group of cryptographic transformations on a given set of keys does not increase cryptographic resistance during repeated encryption. It is necessary to increase the length of key or increase the length of encrypted block during re-encryption to bypass this limitation. The encryption algorithm using the modified method is described by expression that we are watching on this slide. As shown on this slide, the encryption result depends on two blocks. Thus, it's necessary belongs to both keys for encryption and decryption information. Accordingly, the length of encrypted block will be doubled, thus increasing the complexity of cracking the cryptographic system. Usually, to improve the quality of pseudo-random sequence in block algorithms, a model sum 2 bitwise addition operation is used. This approach is not acceptable for multi-key encryption because the text cannot be recovered. Shifting the information blocks before applying the model sum operation is suggested to improve the encryption quality. On slide, we are watching in the second stage of encryption. It's shown that the result of encryption of the second block will be the decryption algorithm using the modified method and described by the expression there is shown on slide. By analogy, information is encrypted and decrypted with M keys. The length of the key will increase in proportion to the number of encryption steps. At each of the stages of encryption, different cryptographic algorithms can be used with the same or multiple sizes of blocks of information. In the proposed approach to improve existing cryptographic algorithms, multi-operated cryptographic coding operations can be used instead of the modulo sum 2 operation. This will be ensured to multivariable of combination encrypted blocks. This modification technique of block algorithms provide good statistical properties of encrypted data. The modified approach protects the keys from known key attacks. Compared to classical multi-round encryption algorithms, it is possible to parallelize the encryption and decryption processes in the proposed methods. Um, Thanks to combining the stages of encryption with several keys. The article proposes a cryptographic method suitable for improving encryption algorithms. Its main property is to increase cryptographic resistance by increasing the length of the key and the length of the block of information. Compared to existing block algorithms based on multiple round encryption, it has been established that the proposed approach will reduce multi-state encryption time to one round of encryption. Accordingly, the description time will be reduced to the execution time of two rounds, the encryption round and the decryption round. Thank you for your attention.